Okay, can you hear me? Sorry. I think we're going to get started. So thank you for showing up so early, and I hope everybody's doing really well. I had a really bad flight yesterday, so I feel very tired, but hopefully my co-presenters will sort of compensate for my performance possibly. So the art and pitfalls of fMRI processing. I'm going to have the privilege. I actually just going to tell you a few general introductions and some very simple theoretical considerations, I think. And then the co-presenters, they're the people who do the real hard work, and they actually talk about work they did in this field. And just a general background for this course. I think there's been a general methodological turn in the biomedical imaging neurosciences. I mean, just my very subjective review is that a few years ago there was a double dipping debate about type 1 error inflation. Then pre-processing has become sort of a more hot topic recently because of systematic biases in resting state research, particularly with motion that people have found. And it's funny, that was the feedback last year. Somebody complained that we didn't call it the science and pitfalls of fMRI preprocessing. He said, why do you call it an art? And we thought about it, and I think art is still the right term because it's not really a science yet. I mean, there is already vigorous methodological debate, but I think it's still sort of more at the art stage. So the purpose of the course is the following, and it was slightly adjusted after last year's feedback. Last year, we were told that you made this too methodological and too research-oriented. You should do it much more basic. So today it's going to be all about basic skills, and you're going to hear about standard pre-processing tools and software. That's going to be the main focus. And then ideally, this will enable you, if you want to engage in some methodological research yourself. And I think the motto, is that with advanced methods in general, comes the need for thorough methodology, but then also there's a feedback that for doing good methodology, you also need to understand the methods very well. And this is today the first part, understanding and being able to apply the methods. And we have a great lineup of speakers. So as I said, I give you I have the luxury of talking philosophy a little bit, but here my co-presenters are going to go through all kinds of artifacts systematically, and then at the end, I think we have FSL pre-processing and SPM pre-processing perspective. So that should be, we're very excited. We added that deliberately in response to last year's feedback. Okay, so just starting on the philosophy a little bit, all of this I think is quite obvious, but I think it's nice to maybe sort of recall what we're doing in fMRI. So the raw fMRI signal, and it doesn't matter whether you task-based fMRI or resting state fMRI, there are several kinds of artifacts and factors that are statistical or subject-dependent in nature. Usually slices are, they're not acquired simultaneously. Then subjects might move, subject breathe and have a heartbeat, and then they're just subject differences in brain size and shape. And then there's some systematic effects that come from the scanning environment. All of these need to be somehow accounted for before you do group-level analysis. There's been quite a few reviews now. I really like this one that came out 2 years ago. And it gives a really excellent overview, but what's sometimes not considered, because it's hard to do, I'm not saying it's easy to do, is that there's an interaction between different processing states, and that relative variance considerations are difficult to perform, right? So, in other words, often people will focus on one processing stage, which is already difficult enough, but then they'll necessarily neglect how this interacts with the other processing stages, right? And in terms of differential effect size, it's hard to make a statement. What's more important, to fix your motion regression or your physiological artifact? It's not quite clear, right? So this might be a typical within subject pre-processing pipeline, which I think most people are familiar with. Here there's slice timing correction, maybe realignment for motion, then there's a co-registration to a structural, maybe some bandpass filtering, and then, recently has been more in the awareness of practitioners that you should deal with motion in a better way. So you could do scrubbing or motion regression or maybe both. And if you think about it, what you're doing, you have the raw fMRI signal, which is afflicted by all these processing artifacts or sort of subjective factors, and you are applying these algorithms in kind of a nested way, right? You first do slice timing correction and so on, and you can write it this way or you can write it this way, but you do this nested operation to get at the putative real signal that's free of artifacts, right? And if you do this, there's an obvious optimization quest. So first of all, what are the best ways of doing these processing stages? But then, if you think about it a little more, it's not enough to just fix each one. You also need to get the order correct, right? Why is that the case? Well, if you look at this kind of nested formulation where each processing stage happens in a successive manner, you see that this cannot be true because, first of all, different artifacts interact with one another all the time, right? For instance, slice timing, corrections and motion, right? They'll be interacting. People will be moving as the volume is acquired. And these artifacts are happening in parallel all the time. You can't break them out neatly into sort of nested mathematical operations. So if you reflect a little more, it follows that unless all these functions are linear, which they will not be usually, right? If they're not linear, then the ordering has to be optimized because the ordering of this will matter. And there is no a priori optimal ordering that's available. That's a real empirical sort of optimization quest. We will not do this today. As I said, today we'll focus on the basics, but I just want to bring it to your awareness. And some people have dealt with this already for task-based fMRI, which I'll quote later. Okay, so there's a further. So I think this is kind of important, and it's kind of further. If you optimize your processing pipeline, it might very much depend on whether you do task-based fMRI or whether you do resting fMRI. And if you do task-based fMRI, it also matters what task you're doing, right? Because in task activation, usually you look for some kind of correlation, of here we have a time series of a voxel, denoted as X, and we have D, that's our design vector, right? It sort of incorporates information about the task, And you'd see that this is a first order moment, right? Usually D doesn't change by, the task information doesn't change isn't afflicted by any of these noise sources. Whereas in resting state fMRI, for instance, you're dealing often with functional connectivity, So there we take two voxel activities that are correlated, and that's a second order moment. And if you just, this kind of pseudo-mathematical sort of notation will show you, if you have task-related fMRI, and imagine all my pre-processing parameters, all my knowledge is embodied in these parameters U, so you see, if you differentiate this with respect to the parameters U, you only have to take care of the voxel activation, right? Whereas if you have resting state fMRI, now we have a product of two voxels. So each of them is afflicted by the pre-processing chain. So this already tells you that what works very well here, imagine you could do this in a simple variational fashion. You could come up with a gradient that is 0 and you have the best way of optimizing. Then this, if you figured out your task-related fMRI, this will not work or in general, this might not work for resting state connectivity and vice versa, right? Okay, so let's recall some of these simple theoretical insights. Sorry, I'm having a little trouble here with it. Okay, so it follows breaking out the pipelines into separate modules is strictly speaking incorrect, but it's the easiest thing to do right now. We're gonna have to do this. There's no a priori optimal ordering, right? Optimization has to ideally be made empirically using some performance metrics. And then the optimization of first order signal moments, which is usually task-related activation, might give you quite different results from higher order moments for resting state connectivity. So what works very well for task-based fMRI. You know, imagine you have a work-in-memory task, you optimize your pipeline, you're very happy with it. It doesn't follow automatically that you can apply the same settings to resting state fMRI, right? Okay, so this is again, so this is why I say this is all somewhat speculative and theoretical, but imagine today you walk away from here and you say, oh, I really want to optimize my processing pipeline, and there are tools available. You have to look at these three things. Which tools do I want to use? What parameters and what order? And then there's an additional question is, what quality of criterion should you use to inform the judgment of good pipeline performance? What does it actually mean if a pipeline performs well, right? And there's several, I mean, these are some ideas, they might not be the only ideas, but if you have simulated data, right, you have the gold standard knowledge. You know exactly what are false positives and false negatives. So you could try to minimize the false positives and false negatives, pick a pipeline that really works well. You could also do something like residual sum of squares for the time series, right? So in simulated data, you have the luxury of knowing exactly what you put in, right? But simulated data requires a simulator that's somewhat realistic. I think there's some products out there, but I won't discuss them today. And then in real world data, it's a little more complicated, because in real world data, you don't know what the real gold standard sort of ground truth is, really. So you could look at some metrics in real world data. For instance, if you split your data, you want to make sure that you replicate the activation that you find in one data fold and you find it in the other, right? The same with functional connectivity. If I find functional connectivity in one data fold, ideally I want to find the same stuff in the second data fold. So you can maximize this kind of replication. Then you could also look, how does the replication quality in your data, how does it correlate with primary measures of interest? And ideally there is no correlation there, right? So if you find that functional connectivity, imagine you're interested in default mode connectivity, and you compute this in your data, but then you see that the degree of connectivity is somehow associated with the quality of replication for that particular subject, that would give you sort of alarm bells. You know, it means that your primary measures of interest should not be confounded by the data quality, basically, right? And then the last thing is, there is some ground truth available in task and even in resting state fMRI. There is usually subject identity or task identity, right? In resting state fMRI, you might not have a task, people are not doing a task, but you know, if you have several subjects, you know who's who, and you can see whether you can predict subject identity on the basis of a classifier derived in one data fold and see how well that works in a second data fold, right? So that could be maximized also. All these metrics could be used. But as I said, you know, this is just my subjective review. There might be other ways, and you know, these metrics embody a priori value judgments, right? You can combine them in certain ways, you know, and they might also give sometimes contradictory results. Although I haven't personally seen that, but it's possible, right? Okay. So this is just some way of thinking about pipeline optimization, and as I said, I'm just going to leave you with these questions today. Most of those questions will not be answered. Some of them will be, but not the question of the whole pipeline dependence. But just to recall what you want to, if you embark on your own research process, you're going to look at what is the best pipeline for removing artifacts. You know, the pipeline constitutes algorithms or procedures, and the order matters. Then, as I just mentioned, the metrics are important for judging good performance. That's sometimes not so easy, particularly in real-world data where you don't know the ground truth. And then there are also questions you could ask yourselves, maybe should some standard tools be left out entirely because they cause more problems than they solve, right? That could also be the case, and I think there's some examples in the literature recently where that has been the case. So all of these things are worth considering if you embark on your own methodological research project. So So some of this has been done already quite well for task-based fMRI. I don't think, but you could easily take this and adapt it to resting state fMRI also, but there's a whole analytic framework also with software support called N-pairs, non-parametric prediction, activation, influence, reproducibility resampling. And this has been pioneered by Stephen Strother and his co-workers and students. There are various places where you can get the code. There's one on the Nitric site. They also have a Google code site. And so this has done some of the optimization using some of the metrics I discussed today for task-related fMRI quite well. Okay. So I just want to show you one example, and it's a very simple example. The details don't matter very much here. But I can show you one example of a clear artifact in the data. So this is also the details of the study don't matter very much, but this is in 167 community-dwelling elders, age 60 to 80. And we just we did standard pre-processing and got 90 ROIs from the automated anatomical labeling atlas. And we could do some split half estimation of how reliable the global connectivity is between data folds. We can quantify this with a metric called eta squared. And then we have one outcome of interest. We take connectivity within the visual resting state network. And as I said, the computational examples are not very important. What ROIs were included here isn't so important. But what you can see here clearly is here, if you look at the eta reproducibility metric, so the bigger eta, the better the reproducibility is between two data folds. You know, everybody's time series was split up in two. And you see that the connectivity in the visual resting state network correlates kind of rather strongly with the eta reproducibility metric. So the data robustness really influences the correlation strength, giving you sort of a bias. So this is clearly an example that makes you worried, and I put some word from my native German in there that many people will know probably, Scheiße. So the connectivity that you're interested in a resting state network, you want to, sort of investigate, with relation to outside sort of external demographic variables. This is clearly confounded by the data quality, so that's a problem. And that can happen quite easily, I think. Okay, so I'm very excited to welcome the first speaker, and today Blaise Frederick couldn't be with us, which is a real shame. We miss him, but we have a worthy replacement with Yunji. And please, hopefully you give good feedback, but even if you don't give good feedback today, please make your feedback constructive. We want to improve the course and make it relevant to all of you. And I think we're doing quite well in time. I don't think there are any questions here. So I'd like to move on, ideally, to the first speaker.